Alright, so in this video we're going to talk about just a brief introduction on finite element methods. So this course is not supposed to go through everything that you need to know about a finite element methods. However, this is just supposed to give you an overview of what finite element methods are and some of the basics behind finite element methods. So the first thing is typically when we're modeling a system, we start with some type of continuous structure like this, and then we can so what finite elements does is we take a continuous structure and we break it into smaller but finite elements using matrices. Okay, so basically we took this continuous part and we broke it into 1, 2, 3, 4 elements. Okay, and the elastic behavior of the elements is defined based off of the geometry of the element, the material the element is made out of, the loads and displacements that are applied at the nodes, and then if there's any force that's distributed within the element. The nodes are where the elements meet other elements. So in this case, we have 1, 2, 3, 4, 5 nodes within this structure. Okay, and at the nodes are where your boundary conditions are applied and your external body forces are being applied as well. Okay, so in this case, our boundary condition would be there's a fixed at part 1, and at where the force is being applied, we would have our external force would be there. So each node possesses up to 6 degrees of freedom. So you can have translation in x, y, and z, and then you could have rotation about the x, y, and z axes. Okay, so in general, how finite element analysis works is that you're going to define each element in its matrix form. Then what you're going to do is you're going to combine every element to create a global matrix that will define the forces and displacements across the entire system. Once you apply those forces across the whole system, once you assemble that global matrix, you can then apply your loads and boundary conditions to simplify the matrix down. And once you have your simplified global matrix, you can then solve for any unknown displacements within the beam, any unknown reaction forces. And from the displacements we talked about earlier in class, you can get the strain within the system, and then you can use the strain to then determine the stress. All right. So finite elements does have some limitations. It is not a perfect system. It can only be used for linear elastic materials, or at least then the theory that I am presenting can be used for linear elastic materials. So it has some limitations. So the major errors that often come up in FEA are computational errors, which are typically due to rounding errors, but I would say for the most part, most finite element analysis software does a pretty good job of accounting for any computational errors. But the major thing that finite element errors that you need to be aware of is something called discretization errors. So, for example, if we have a part that we have shown here, all right, finite elements do a good job of estimating some smaller non-curved surfaces, but when we discretize our part, the curved surfaces of this part are difficult to model in finite elements. So like, for example, our circle becomes more like an octagon, and then our curved surface becomes more like a collection of straight lines. So if you have a surface that's well meshed, it's difficult to sometimes account for it using the finite elements. So depending on the geometry, right? and then I guess the other thing that finite elements does is it assumes the strains are throughout the element are often referred to as being constant, and sometimes that this is not enough to account for rapidly changing strain fields. So if the finite elements are too large, then you might not accurately predict the results. All right. So so what you can do, or the one thing that we're going to talk about, or you should be aware of, is that there's different types of finite elements, and depending on the type of problem that you're trying to solve, will help you decide what finite element is the most appropriate to help you solve the problem. So for in the case of in this class, we're going to focus on just 1D elements. So we're going to focus in on truss, which are often called bar elements, and beam elements. Okay. But depending on the application and what you're interested in, other finite elements would be maybe suitable or needed. So, for example, there are surface elements, which are both in triangular and quadrilateral form, and then there's also hexagonal, and then there's also 3D elements, which are solid elements, as well. So depending on the application, you can select the most appropriate element that would best model your surface. So you always want to try to pick the simplest method, or simplest element with like the least number of nodes, if possible, to minimize the amount of computations. Because the more nodes there are, the more the harder it is to calculate. The larger the calculations will be. So you want to use the simplest element that will allow you to get the most accurate answer. All right. So it's always about a compromise in the choice of elements. All right. So we're going to talk about some very basic things for finite elements. Okay. So in the case of we're going to talk about the bar element first. So the bar element is a 2D element that has a node on both sides. All right, so it has one node on both sides of the element. It'll have node I and node J, and it can have a force being applied to it on both the left and right hand side, and that force is going to cause some type of displacement for both of the nodes, which will denote as UI and UJ. So using our definitions of strain energy, we can actually calculate our the strain within our system. So we'll end up getting that the strain energy is going to be equal to 1/2 the stress matrix times the strain matrix. So if we get that, so we can say that that our stress matrix transposed would be equal to U of I times Uj, and U of E, or E over L, E times 1 and -1. So if we plug in this equation here into the matrix, we can then solve for our strain energy, and what we end up getting is what we'll end up getting is we'll have our sigma t, or will be here, and there's a typo here. There should be a -1 and 1 here. All right, and then there should be this term here is our elasticity, or sorry, not our elasticity, our strain matrix. So if we take, we can simplify this down further, and what we end up getting is we end up getting this for our strain matrix, because if you notice, none of these terms here are a function of x, so we end up just getting this value for our strain energy here, and our strain energy, where this K elasticity matrix is what we refer to as our stiffness matrix, and that's going to be equal to Ke, which is a constant, times 1, the matrix of 1, 1, 1, negative 1 on the first row, and negative 1 and 1 on the second row. So the stiffness of the element is equal to the area of the element times the elasticity of the element divided by the length of the element. Okay. So, so from that, we go to the next page here. We can also define the work done on the element. All right. So the work done on the element will be due to the displacement at each end, times the force applied at each end. Okay. So if we apply a force on each end, it'll create a displacement from the original location to the new location. So we can, and that would be the sum of those two combined will give us our total work. And then the last thing that I'd like to mention is that talk about the notation within these systems. So we have for the nodes, so they're typically, we're going to use the letter I to describe the nodes. So at each node, there'll be n nodes within the system, the total global system, and at each node there will be a nodal force, which will denote with the lowercase f, and there can be nodal forces in the x, y, and z directions in a finite and finite elements, and then for the at each node there's also displacement. So there'll be a node for each node could be displaced in the x, y, or the z direction. So for elements we'll use the letter E. Right, so there could be there could be up to p number of elements in a system, depending on the type of depending on the type of element you have, there might be a different amount of nodes. And so the things that you need to know for an element is you need to know what is the area of the element and what is the length of the element. Okay, so typically we might refer to something as like displacement with a number and another number on the outside. The number on the inside would correspond to the node. The number on the outside would correspond to the element.